Welcome to my GIS lab. In this video we will discuss latitude and longitude, UTM projections, and the key properties of projections. When we look at the concepts of latitude and longitude, only one of them was provided by our rotating Earth, the equator. But in order to define a coordinate system, we also need an origin point for our longitude. It's a long story, but eventually Greenwich in London, England, became the globally accepted location defining the prime meridian, the meridian of zero longitude. The original location was later corrected to be about 100 meters east of where the observatory is, somewhere in the park. Now we have a coordinate system origin somewhere off the coast of Western Africa to which we can relate all locations on Earth. Where our prime meridian meets the equator is the origin of our coordinate system. So from there we can relate all other locations on Earth. We can define lines that are circling the Earth parallel to the equator, therefore called parallels. Parallels inform us about our latitude going north or south, using the equator as a natural original point. They go to a maximum of 90 degrees north and 90 degrees south. Or, if latitude and longitude are expressed in a spatial database, then we use plus 90 degrees for north and minus 90 degrees for south. Meridians inform us about our longitude going east and west from the prime meridian. Longitude has a maximum of 180 degrees west or 180 degrees east. And again, if we were to express these in a spatial database, we would confer to 180 degrees east as being plus 180 degrees, and 180 degrees west would be minus 180 degrees west. So everything west of Greenwich, London has negative longitudes. When we look at the Earth from the top, we see the full circle of 360 degrees. Here is Greenwich, and here is a dateline at the opposite side. When we look at the opposite side of our prime meridian, we see the location of the dateline. When the sun is highest on any given day in Greenwich, the dateline is turned away from the sun, and that is where every new day begins. And every hour the new day begins 15 degrees further west. So when a new day starts at midnight in Alberta, it is already 7 o'clock in the evening in New Zealand. In this, the World from Space projection, we see the latitude and longitude origins used. The latitude is 70 degrees north of the equator and 40 degrees west, so we use negative values, from the prime meridian. Let's look at an important property of any projection, the conservation of shape and size. We have already seen that the shape of Alberta changes depending on which projection we use. Here I have added circles, all of identical size, at various locations around the globe. We can use these circles to see how they change when we use different projections. Let's look at some examples. Here is a standard display of spatial data expressed in latitude and longitude, the GIS 1984 projection. You want to use this one if you have data in lat long and you have no additional information. As you can see, our circles look like circles only at the equator, as there is no distortion there. But the further north we go, the more the circular shape is distorted and the size is becoming very unrealistic. This is the reason why Alberta looks stunted in this projection. The Mercator projection is a very old projection used for navigation. It was used for navigation when global trade was carried out by sailing ships. It has a very interesting property, which is that angles are preserved and therefore shapes. The loxodrome is a line that crosses all meridians at the same angle, which made navigation very simple. For example, traveling from Georgetown in Guyana to Porto in Portugal to bring sugar, coffee, and tea, the captain only needed one single angle. But the consequence is a massive change in size, especially in northern latitudes. Here, Greenland is about the same size as South America, when Greenland is actually over 8 times smaller. For many years, this or similar maps were used in TV news, informing the viewership of a very wrong concept of the size of countries. Canada, Europe, and especially Northern Europe and Russia are massively oversized. The Lambert equal area projection is used to display Canada with its true areas but small distortions in shape. When we zoom out, we can see that the circles are the same size and almost circular at locations close to Canada. Here we can also see the date line again and deviations from the 180-degree meridian in order to keep the same date within a country, such as Russia and Alaska, to include the American islands in the Bering Strait. And then we have some very specialized projections, such as the nonomic projection, which is used in international aviation. It connects locations on the globe with straight lines, such as a connection between Calgary and Frankfurt. And finally, we have global maps that you may remember from high school, trying to compromise between angles, sizes, and shapes, such as this Mollweide projection or the Robinson projection. Now that we understand that shapes and sizes change with projections, we see the challenge to make projections accurate where we work with scales that require meter or sub-meter accuracy. That has implications for projections used in Alberta. Here we see the distribution of all UTM zones from number 1 in the very west to number 60 in the very east. Of interest to us for Alberta are the 2 UTM zones 11 and 12. So let's have a closer look what happens with zone 11. So here is zone 11. Let me turn off the other UTM zones. And I also will turn on the central meridian for zone 11. That is our yellow line. And if we now add the equator, we have our coordinate system. At the equator, that represents our x-axis. So here we have easting values, and the yellow line represents the y-axis. So that would define our y-coordinates or our northing values. Let's have a quick look at the coordinates at our origin. If I hover my mouse here over the intersection between the two axes, we see that it's virtually 117 degrees west or minus 170 degree longitude and 0 latitude right at the equator. If we want to display this in meters, we have to first change our coordinate system, because if I go to the general button in my map properties, I cannot change my display units to meters because my map units are in degrees. It's angular units for lat long, of course. So we have to change the coordinate system to UTM 11. We find that under UTM projections, under NAD 83 projections, and we choose UTM zone 11. And in our display, we can see that, of course, the UTM zone is widest at the equator and narrows towards the North Pole. And here is my origin. When I change now my general button again here, now I can change my display units to meters, because the map units of UTM zones are always in meters. And I hover my mouse over the same origin, and it is virtually at 500,000 meters east. That's our set false easting, and 0 north, which of course is at the equator. And when we look at the UTM zones globally, we can see that they are widest at the equator, and then as further north we go, the narrower the UTM zone becomes until it is very, very narrow up here. And that causes a little bit of challenges when it comes to handling XY coordinates in Alberta, for instance, because the X coordinate will be different in length than the Y coordinate. That's all for now. I'll see you next time.